Hi everyone, my name is Andres. First, I would like to thank the organizers for inviting me to the NCNGT conference. So in this video, I'll be talking about understanding the geometry of some link complements on circle bundles over hyperbolic surfaces. Currently, I'm a postdoc at the University of Helsinki, and this is a joint, some of these results are joint work with Tommaso Cremacci and Andrew Germall. So as a brief introduction, thanks to the uniformization and classification theorem of surfaces, we know that every oriented surface admits a geometric model that can be spherical on the Euclidean plane or in the hyperbolic plane, right? The analog in three-dimensional manifolds, it's a result due to Perelman and Thurston, which states that every compact three manifolds admits canonical decomposition in geometrical bases, and the geometrical models are just these 8. And 6 of them, not the hyperbolic and the sol, are already topological classified, known as Seifert-fibered spaces or circle bundles over surfaces, and basically will be the ambient manifolds from which we'll be removing these links. These are obtained simply by taking a circle trivial bundle over a hyperbolic surface with some holes, and then gluing along the boundary of these surfaces some solid toroid. And the others that manifolds that admit a hyperbolic structure are still a big field of research. So to give some examples, we have some come from link complements on the sphere. Other can be obtained as a mapping torus of an anosov diffeomorphism over a hyperbolic surface. So due to Thurston, we understand which topological characteristics the three-dimensional manifold has to achieve in order to admit that structure, geometric structure, and it is simply that it is irreducible, meaning that every embedded sphere bounds ball, its fundamental group has to be infinite, and every pi1 injective tori has to be parallel to the boundary. So as a toy example that will help understand the families of examples that follows, I take, for example, let's consider this three tori, which happens to be obtained by identifying opposite faces of this cube. And we see that this is not a toroidal because it has the faces are incompressible toroid, and moreover, we can find non-isotopic to these three, like this purple one. So in order to make it hyperbolic, we are going to remove some links. So first, if we remove an unknot, we see that now we don't have the property of irreducibility because this all encloses the knot. And we can read that from the projection to the base because this loop is null homotopic. So we're going to start removing other kind of links. So to prevent the existence of this horizontal torus, we're going to remove this vertical fiber. Then this vertical torus, we're going to remove this fiber. And for this frontal torus, we're going to remove this fiber. So what we see until now is that the projection, well, we can see it as a punctured torus, and it has two filling curves. We also point out that if we add a parallel copy of one of them, then there will be another incompressible toroid which encloses these two of them. So to have only one homotopy class of each one of these components, we're going to say that the projection has to be a geodesic, a closed geodesic. And well, this family of closed geodesic is filling. And these are kind of the families that we are going to construct. So why this is a toroid? Well, simply the idea is to take the universal cover of the three tori that it's here, and then remove all the pre-images under discovering of the link. And by pointing out that this is a free group, that implies that it doesn't admit an embedded by one injective toroid, or C2 cannot be a subgroup of this free group, right? So in general, how we construct these link complements are first just to pick a surface and a circle bundle, then a collection of closed geodesics oriented, and then just take lifts of each one of them, of each component, into a closed knot. And this is how we construct our links. So there can be many choices of them. To give an example, if your Seifert-fibered space is a trivial bundle over a hyperbolic surface, then we're going to say that a link is stratified if it can be partitioned into cyclic order set of sublinks, and there exists a pairwise disjoint collection of global sections, such that each sublink is embedded into this global section. Otherwise, we're going to say that the link is unstratified. So one remark is that the projection of these sublinks into the base surface of each one of these sublinks is a multicurve of closed geodesics. It can be, so this is that one. More details about these examples, you can find it in the Andrés video posted also here. So another family which is very interesting is considering periodic orbits of the geodesic flow. So here our Seifert-fibered manifold is the unit tangent bundle of the sphere, and the links are obtained by taking the lift, which represent the position and the speed of the closed geodesic. This has already been studied by many people like Gis, Deornois, Kelmer, Sarnak, Biermann, in the particular case of the modular surface. And for example, the unit tangent bundle in this case, it happens to be the complement of the triple knot on the sphere. And another fact is that if you have a punctured sphere, then the unit tangent bundle is the trivial bundle over the sphere. So as I promised, I'll be interested in understanding the links complements. So a nice result that I obtained with Tom is that there is a nice characterization of when these manifolds admit a hyperbolic geometry, and it is just in terms of the combinatorics of the geodesics in the surface, and the properties that they have to be filling, meaning that if I cut along these curves, I obtain a bunch of disks and puncture disks. So this is an example of a filling close geodesic, and by Mostow rigidity theorem, every geometric invariant is a topological invariant. And so as these sessions are about volume, then we'll be interested in finding an effective and computable estimates for the volume of these link complements in terms of the combinatorics or properties of the closed geodesics in the surface. So the plan first will be to give some general bounds The upper bound will be in terms of the self-intersection number of the curves, the lower bound in terms of some homotopy classes. Then focusing more in the canonical lifts, I'll mention some known upper bounds in terms of the length and show that we can obtain some lower bounds for families of closed geodesics, also in terms of the length. And finally, this third topic, combining the properties of being a stratified and a canonical lift, we finally found quasi-isometric estimates of the volume in terms of combinatorics of the curve distance and path distance. So, and this the third point, you can also find it in the Andrés video. So please check it out. So the simple part of this problem is finding an upper bound, because the task is just to find a triangulation, an ideal triangulation. With Tom, we did that in terms linearly of the self-intersection number. Moreover, we found that if our manifold was a trivial bundle, then we can construct sequences of family where this bound is optimal. And so how these families of links and geodesics are constructed. So simply take, for example, here we consider the puncture tori, then consider a geodesic where while you travel along the geodesic, the intersection, you can alternate colors to white and black. So if that is possible, then you can lift it into a global section and then adding some crossing information in these alternating points. So I want to point out the difficult part of this theorem is in this lower bound, which was obtained by using some results of how we Purcell. And this is the quasi-isometric constant in the lower bound. It depends on the genus of the surface. So this is in general not optimal, because we can construct families of canonical lifts where this self-intersection number it's not a good bound, meaning that the sequences of volumes, it's bounded, the sequences of manifolds of link complements, it's not homeomorphic, and the self-intersection tends to infinity. So these are basically obtained by taking a closed geodesics and then concatenating another closed geodesic in an intersection point which is carefully chosen. So this is the first iteration. And then what we are going to do to obtain the sequence is winding more times along the second one. What we can also point from here out is that if we cut along a Pans decomposition, even though the number of arcs is increasing, the homotopy classes of them is fixed. And that is just the invariant that we obtained for the lower bound, which, as I repeat, it's a more difficult result, and it was obtained by using a result of Agel, Thurston, Sturm about finding incompressible surfaces. So here's what I mean about different homotopy classes of arcs, and this is the same. No, this is different and the same homotopy classes of arcs. This is not optimal, and this was a consequence of a joint work with Tom and Andrew. We saw that for every for every stratified link, first of all, the volume is quasi-isometric to some invariant depending on the inf of the sum of the Pans distances when the inf runs over the Pans decomposition, extending the projections of every sublink. and this induces an ordering in the sum. And the homotopy classes of all these examples is bounded just by the topological type of the surface. So in the case of canonical lift complements, there is a result by Bergeron, Pinsky, and Silverman, which by fixing a metric on the surface, they were able to bound linearly from above the volume in terms of the length. And then they made some experiments with brands, and for a finite set of closed geodesics in the modular surface, they found that the volume and the geometric length behaves linearly, the same. So a good question is if we can find an infinite sequence of closed geodesics such that the length tends to infinity and the volume is bounded from below by the length. And by using our combinatorial bound that I have mentioned, we were able to do so up to some logarithmic factor. And the idea of the construction is fix a length and then pick all the one representative for each homotopy class of this bounded length and concatenate them all together. So that's how is obtained the family of closed geodesics. So this length bound is in principle not optimal because one can choose any diffeomorphism of infinite type, and by considering the canonical lift complement of a closed geodesic, and then the canonical lift complement of any iterate on the diffeomorphism, we will be obtaining homomorphic manifolds and by Mosteau with the same volume, even though the length, if we fix the metric, the length goes to infinity. A more interesting result of why the length is not optimal is obtained by varying the metric allowing that. So we found none, and come from the examples of the self-intersection number of why this is not that I mentioned also. So they are basically the same examples. But here we have just that we can vary the hyperbolic metric for each element of the sequence. And even in that case, the length will still tend to infinity. So a nice result that I found with Andrew and Tom is that for complexity one surfaces and any collection of simple closed geodesics, these two concepts of being stratified and canonical lifts join together because the canonical lift is going to be stratified in this case. And moreover, there we found a quasi-isometric estimate of the volume in terms of the sum of the curved distances of consecutive geodesics where the order is given by the stratification. And here is a picture of the curve complex and the curves in each one of these vertices. And another nice result, a good result, is that for every filling pair of simple closed geodesics on any surface, we found quasi-isometric estimates for the volume in terms of the inf over the bands extending the first and the second curve of the bands distance of these two bands decompositions. Notice that this is a lot harder result because the canonical lifts maybe are not stratified, and here are some examples of pair of simple closed geodesics which are their canonical lift is not stratified. And actually we found that the condition is a topological condition on the base, meaning that if I take the complement of this pair of curves in the surface, I obtain geodesic rectangles and pointer disks. Finally, in trying to put together these two results for some surfaces, we found hyperbolic metrics and sequences of filling pairs of closed geodesics where the combinatorics, the curve distance tends to infinity, and the volume is a quasi-isometric estimate of the curve distance between these two curves, and moreover, relating with the length invariant, is quasi-isometric to the log of the length. Basically, all these closed curves are obtained by taking finite covers of the 4-puncture sphere and the 1-puncture tori. So a global picture of how I'm seeing this, the progress on this research is that we have the lifts of filling close collections of closed geodesics. We have an upper bound in terms of the intersection, self-intersection number, a lower bound in terms of the homotopy classes in general. There are some families which are called the alternating knots, where the self-intersection number is an optimal bound. Other families known as stratified lifts, where the volume it can be put it in terms of an expression of the band's distance. And the thing that we know for canonical lifts is that we can improve this intersection upper bound by the length. So thank you for looking to this video, and stay safe.